Hello, my name is Dr. Steele, and welcome to Steele Mathematics, where lessons in Algebra 1, Geometry, Algebra 2, Pre-Calculus, and Calculus are taught. And today, we are going to talk about radicals. Now, when we're talking about radicals, we're talking about higher index radicals. So with that being said, I want to start off reminding you what each part of a radical is. First, we start with the radical sign. The number that is inside the radical sign is called the radicand. So, for all your mathematical lives, you see the radical sign and the radicand. And that means square root. But I want to introduce to you something new. You will see a smaller number inside the pocket, which is called the index. Now, what does index actually mean? Well, I'll show you. The nth root of m, and that's how it's read, the nth root of m equals a, if and only if a to the nth power is m. Now, I want to show you some examples so that the definition is clear. Of course, the square root of 49 is 7. Now, notice you don't see an index there. If you don't see an index, the index is really 2. Next, we have the cube root of 27. And the cube root of 27 is 3 because 3 to the third power is 27. Next, we have the fourth root of 625. The fourth root of 625 is 5 because 5 to the fourth power is 625. What you just saw in the first three examples are perfect powers. 49 is a perfect square. 27 is a perfect cube. And 625 is a perfect fourth power. But suppose that the powers are not perfect. Let's say you have the square root of 50. The first thing you may want to do is you're going to list all your perfect squares until you get over 50. So you got 1, 4, 9, 16, 25, 36, 49, 64. We're going to stop at 64. So what you're going to do is you're going to look at the highest perfect square that can go into 50. And 25 is that number. So what you do is you factor the square root of 50 as the square root of 25 times the square root of 2, because 25 times 2 is 50. The square root of 25 is 5, but you can't take the square root of 2. And therefore, your solution is 5 times the square root of 2. Next, we have the cube root of 24. And 24 is not a perfect cube. So let's list our cubes. We got 1, 8, 27, and we're going to stop here. And the highest perfect cube that could go into 24 is 8. So we're going to factor this as the cube root of 8 times the cube root of 3. the cube root of 8 is 2, but we cannot take the cube root of 3. Therefore, the solution is 2 times the cube root of 3. Next, we have the fourth root of 162. So the first thing we're going to do, we're going to list all our fourth powers. So we got 1, 16, 81, 256, and we're going to stop at 256. And 81 is the highest perfect fourth power to go into 162. Therefore, we're going to factor the fourth root of 162 as the fourth root of 81 times the fourth root of 2. The fourth root of 81 is 3, but you cannot take the fourth root of 2. Therefore, the solution is 3 times the fourth root of 2. So in these first 6 examples, we took the roots of regular numbers. But what about exponential expressions? Let's say you want to find the cube root of x to the 9th. Well, all you got to do is divide the exponent by the index. Therefore, 9 divided by 3 is 3. Therefore, this will be x to the 3rd. 21 divided by 7 is 3. So this will be x to the 3rd. For number 9, 10 divided by 5 is 2, so this is m to the 2nd. 25 divided by 5 is 5, so this is n to the 5th. Therefore, the solution is m to the 2nd, n to the 5th. So again, all you're doing is dividing each exponent by the index. But suppose that the exponent is not a multiple of the index. Then in this case, you have to think long division. 4 goes into 7 one time with remainder 3. The quotient exponent goes outside of the radical sign, whereas the remainder stays inside. Therefore, the solution is k times the fourth root of k to the 3rd. Next, we have the 7th root of x to the 25th, y to the 14th. Well, 7 goes into 25 3 times with remainder 4. And 7 goes into 14 2 times with no remainder at all. That's why you're not going to have a y inside the radical sign. Therefore, your final solution is x to the 3rd, y to the 2nd, times the 7th root of x to the 4th. All right, next to number 12, we have the 5th root of n to the 27th power, p to the 19th. Well, 5 goes into 27 5 times with remainder 2. 5 goes into 19 3 times with remainder 4. Therefore, your solution is n to the 5th, p to the 3rd, times the 5th root of n to the second p to the fourth. So we talked about finding roots of regular numbers, and we talked about finding roots of exponential expressions. So let's put the two together. Let's say you're looking for the cube root of 8x to the 27. First, the cube root of 8 is 2, and 3 goes into 27 9 times. Therefore, the solution is 2x to the 9th. On number 14, we have the cube root of 64, x to the 10th, y to the 12th. Well, the cube root of 64 is 4. 3 goes to the 10 3 times with remainder 1. And 3 goes into 12 4 times with no remainder. Therefore, your final solution is 4x to the third, y to the fourth, times the cube root of x. Finally, we have the cube root of 54, u to the 14th. Now, 54 is not a perfect cube. So the first thing we're going to do, we're going to list our perfect cubes. So we got 1, 8, 27, 64, and we're going to stop right here. And 27 is the highest perfect square, or excuse me, perfect cube that can go into 54. So we're going to split 54 up as the cube root of 27 times the cube root of 2 times the cube root of u to the 14th. The cube root of 27 is 3, but you cannot take the cube root of 2, so it stays inside the radical sign. 3 goes into 14 4 times with remainder 2. Therefore, your final solution is 3u to the fourth times the cube root of 2u to the second. So what we learned today are how to simplify higher index radicals. To do numbers, you just find out what do you raise to that power to get the radicand. And the radicand is not a perfect power. You find the perfect power that goes into it. As far as exponential expressions go, all you're doing is just dividing each exponent by the index. I hope that you have a wonderful and blessed day.